All right, so welcome back, everybody. Sorry about kind of a last minute change. I know it's kind of not great to change things last minute and kind of moving an in-person class to Zoom all of a sudden. But since traveling back from Spain, I got a little bit sick, and yeah, I tried to be cautious, but I think it's getting worse. And I also got some emails from people who are getting contacted by COVID and all. So I just wanted to make sure that we're all staying safe. So my apologies, but hopefully we can have a good class today on Zoom. For those of you guys who have honors section after this, we're gonna keep the same Zoom link and we're gonna talk about the honors section afterwards as well. So stay online for the honors section. Okay. Does anybody have any questions? You can either use the Q&A part of Zoom or use the chat or just unmute yourself and ask questions, okay? Can somebody just confirm that you can hear my voice?
Yes.
Cool. All right. So last time we talked about kind of designing this, right? So we talked about various different things here, the blue parts and the black parts, and we kind of go over all of it, right? And I told you that the rationale behind designing this is having a data path part and having a controller part. The controller kind of orchestrating the movement of the data. And the big trick that we are using is kind of using this kind of multiplexer selectors that kind of tell us to where to move data, right? So for example, are we selecting from here or are we selecting from here? Same story from here or here and so on and so forth. Probably something that you want to do is going over all each of these blocks and see whether it makes sense for you, each of things that we are doing. This lecture, I'm going to actually do a little bit of more of a review for this as well. Okay. And your homeworks, which we're going to release sometime tonight or tomorrow morning, will be about kind of analyzing this data path and control a little bit more, making some changes and so on and so forth. Okay. So kind of the last thing that we were discussing was this controlled signals. And we kind of show you this. The last thing that we didn't go over was this ALU op. So let's finish this and move on to the next step. Is there any question about this last part before we move on? Okay. So let's talk about ALU op. So the ALU op is a little bit different than other control signals. I'll explain what are we doing first, and then I'm going to explain why are we doing that. Okay. So there is a rationale behind what we are doing, what we are doing, and why we are doing that. Okay. So first of all, as I told you, ALU is this unit that takes two inputs, two n inputs. In this case, n is equal to 32 for us, and then do some arithmetic operation and output another 32-bit value. ALU gets this 4-bit controller called ALU op, and if you look at the kind of the activities that you're doing, remember we are now only focusing on that 10 instructions. Okay, so for load and store, we are using ALU for computing RS1 plus immediate, which was our offset, right? So we are reusing ALU for load and store for computing the address. So the operation that we are using for ALU for load and store should be add. For branch equal, we are doing subtract. The reason we are doing subtract is we want to check whether RS1 is equal to RS2 or not. And if you remember last time, I told you that we have this flag called 0, which is just 1-bit flag that always is equal to 0 unless RS1 is equal to RS2, or in other words, if the subtraction of RS1 minus RS2 is equal to 0. This flag becomes 1. So for branch equal, we need the subtract operation. And then we have all the R type and I type of instruction. And if you remember the list that I shared with you, there were like 4 different things that we are doing with R type and R type. There was add, a subtract, and an OR, okay? So here's what we're going to do for ALU operation. As you can see, we are kind of like having 4 different things. And what we're going to do is we are going to use a kind of a 2-step operation. The reason for this is I'm showing only 4 of these ALU operations here, but in reality, there are many, many more, okay? Since there are many, many more, I have 2 options. Either I have to have to use a bigger ALU operation, or I can use kind of a 2-step approach, the same way that we are kind of doing opcode and func3 and func7. That's exactly what we are going to do for the ALU operation as well. So if you actually look into the ALU op, you will see that we kind of have 3 types of ALU ops. We have 0, 0, 1, 0, okay? And you can see that for all the add operation, this is exactly what we are doing, 0, 0, 1, 0, okay? Then as you can see, we have the sub instruction, which is 0, 1, 1, 0, okay? And again, 0, 1, 1, 0. And then we have all these other ALU operations like 0, 0, and 0, 0, 1, and 0, 0, 2, and so on and so forth. So this is kind of how we tell the ALU, how do we make the difference between these different operations. Again, since these are only 4 different ones, we were probably doing okay with if you only had 2 bits, right? But as I said, since we have more of these things here that we don't show, these other, bits here will be later on used. So the book used 4 bits. I'm going to use 4 bits just to follow the format of the book. But remember, for your own implementation, for example, you can just you can do 2 bits if you want to. Okay. But this is not what we are typically doing. So what we are typically doing is that the controller, okay, only use 2 bits, okay? It's only use 2 bits. And then there is another step called ALU control that kind of generates this 4 bits for us, okay? So what are we doing exactly? If you're looking to this table, okay, we're going to do this trick that we're going to use 0, 0, okay, and 0, 1 for add and for subtract, okay? Since all the other instructions except R type and R type only use add or subtract, we're going to use this trick that we're going to say that controller basically just outputs 2 bits, either 0, 0, 0, 1, or 1, 0, one of these 3 different conditions. And what does this mean is that 0, 0 always means add, okay? 0, 0 always means add. 0, 1 means sub. And 1, 0 means that go and check func3 and func7, okay? So basically, we're kind of dividing checking of the opcode from checking of the func3 and func7. Why do we do that? Because that makes our control decoding much simpler. Because if you see here, we only use the first 6 bits, sorry, the first 7 bits of the instruction. That is the opcode of the instruction, okay? Using the opcode, if you remember, we couldn't tell whether this is, for example, add or whether this was OR, because add and OR was known in func3 and func7 here. So in opcode, we can only tell whether this is an I-type instruction, R-type instruction, load or store or a branch, okay? So what we are doing here is that we're going to say that, okay, I only have access to the opcode here, so I'm going to use this kind of contract. And I'm going to I'm going to output a 2-bit that if it's add, excuse me, I'm going to do 0, 0. If it's a sub, I'm going to do 0, 1. And if it's anything else, if it's an R-type instruction or I-type instruction, I'm going to do 1, 0. Then what I'm going to do is I'm going to send this 2-bit value to this additional controller called ALU control, okay? This is a separate logical unit. This logical unit then use this table. So as you can see, now it gets the func3 and func7. and make a decision to do what exactly, to send exactly what to the ALU. Okay, as you can see, if it's 0, 0, if this left bit is 0, 0, then it basically said that this is an add instruction. Okay, so 0, 0, 0, 0. If it's 0, 1, it knows that this is a subtract instruction. And if it's 1, 0, then it knows that it has to go and check func3 and func7. Okay, so that's kind of the trick that we're going to use in order to tell the ALU operation what operation are we exactly using. Okay, so again, to jump back, if I look from the ALU units, point of view, I only understand 4 different, operation, like 4 different bits as my operation. Okay, and I'm going to have this table to tell me what they are. So 0, 0, 1, 0 is add, 1, 0, 1, 1, 0 is subtract, 0, 0, 0 is add, and so on and so forth. Okay, so from ALU point of view, I don't care how do you create this ALU operation control signal. As long as I see 0, 0, 0, 0, I'm going to do AND. Okay, but how do we create this 4-bit value? We create this 4-bit value in 2 steps. The first step, as I said, is creating a 2-bit value, which we call ALU op. Okay, and then we feed this 2-bit value to another unit called ALU control, and this ALU control then generates this 4-bit value. This 4-bit value is the same as what I've shown here, but the way that we are generating this is the 2-step approach. We takes 2 bits and then make a decision based on that. Okay, the reason for doing this is that makes our controller much faster, because that makes the decoding much faster, because now I only need to take a look at the opcode. Otherwise, what I should have done is I checked the opcode, and then I had to check func3, and then I had to check func7. So that's a 3-step approach that takes much longer for my controller signal to generate a signal, which I don't like. So what I do is that I just say I'm only looking at my opcode. Okay, my opcode will tell me the type of instruction, whether this is R or I or load or store or range. And then I can create all these other control signals as fast as I can. And I'll use another step for the ALU control to kind of like, doing the actual decoding. Okay, so this is kind of the rationale behind the way that we're doing this. Of course, you could have just decode everything directly in the controller. The only difference is that this makes things slightly slower. All right, so let's see if there is questions. Somebody asked, besides the first ALU control, do the other 2 bits come from the instruction to form the 4 bits? So I think the question is from this part. No, this is kind of the contract that we have when we are designing our hardware. You could have easily made, for example, saying that, okay, 0, 0, 0, 1 is and so on and so forth. The reason that we are doing this is if you actually can go back to the way that we are designing logic controllers, we want to minimize the number of zeros, and we want to minimize the number of ones, or whichever we want to design our logic. This is, again, very kind of logic design thing, which I don't want to go into. If you actually read the book, they have a very kind of elaborate table for showing how do we do this. But again, for us, it's mostly just a contract that we know that, for example, 0, 0, 0 is and so on and so forth. Hopefully I answer your question. You can ask your questions directly in the chat. Don't send me a direct message so that other people can see your questions as well, okay? So somebody asked, just to clarify, ALU control is 2-bit in, 4-bit out. Exactly, ALU control is 2-bit in, 4-bit out. So the other question is, so the ALU controller only needs to do something if the ALU op is 1, 0. Exactly, that's why it's very fast. If it sees 0, 0, it knows that it's add. If it's 0, 1, it knows that it's subtract. If it's 1, 0, that's when it actually goes through func3 and func7. That's exactly a good operation. Somebody asked, how does the ALU control generate the 4-bit output? So this is the way that we are kind of designing our FSMs. Think about this as some form of an FSM that takes a 2-bit output and generates a 4-bit, takes a 2-bit input and generates a 4-bit output. Again, this is not just 2 bits, so this is ALU op, so 2 bits ALU op, but it also gets func3 and func7. So the inputs to the ALU control, if you actually zoom in here, you will see that the inputs to the ALU control is these bits of instruction, which is func3 and func7, and also is this 2 bits of ALU op. So the combination of this will help us to create the 4-bit output. So does the ALU look at func3 and func7? The ALU control look at func3 and func7, okay? So as you can see, the inputs to ALU control is this func3 and func7. As you can see, actually, we don't need the full func7. We only need the 30th bit. So we really don't feed the entire func7. We just look at the one after the most significant bit. Another question is, does checking func7 after func3 have a similar check for a certain pattern if it needs to check both? Well, what happens here is that this is not sequential checking. We're going to actually feed all of them together and then create a logic here that as soon as all of these bits are valid, the output would be valid. Okay, this is how we're going to create this. The reason that we didn't do it here is because if I add opcode to this, then my control logic would be very, very complex. So I don't want to do that. So actually, I save number of gates if I do this two-step approach. Hopefully that makes sense. Any other questions? Cool. So that's something for you to kind of check. I know it's a little bit complicated compared to kind of doing a straightforward way of just generating, like looking at the opcode and generating the outcome. But as I said, all of these things are just for saving some logic, okay? Because if I wanted to just look into the opcode and generate all of these things, my control will become very, very complex, and I don't like that, okay? And again, book has a nice description of the actual logic of how this is created. It's actually in the appendix. So if you really want to know how the logic is created, I definitely recommend you to go and check it out, okay? Okay, so that's kind of it for all these controlled signals. So we know that this branch is this one bit that if its branch equal, it will be equal to 1. But hold on, there's another question. So to clarify, you can just use 4-bit ALU op to begin with, and then ALU control is an optional component. Not really. So here, okay, here is a 4-bit value, okay? Here's what ALU understand. ALU understands this and has a table for it that's, based on the 4-bit value, decides which operation to create, okay? But in order to generate this 4-bit value, we first generate this 2-bit value, feed it into the ALU controller, and then ALU controller generate this 4-bit value for us. So ALU controller is really not optional here. It's there for generating that 4-bit value, okay? But we are doing it in two-step approach, as I said, to make things simpler for us. Okay. So let's kind of like finish the discussion to kind of just very quickly go over how the data path would look like when we are doing different instructions. So for example, if you think about an R-type instruction, let's see how kind of the instruction flows into our pipeline. As you can see, the parts that are not going to be used is kind of grayed out, okay? So here's kind of the timeline of an instruction for an R-type instruction. For an R-type instruction, things start from here. Always things start from when we're updating our PC, okay? So the clock comes, the PC gets updated, the new PC, the next instruction is now live. So we go here, we put this address into the instruction memory, we get the instruction after some delay. So this is not instantaneous, there is some delay involved here. Then we have all of these things happen at the same time. I cannot emphasize this enough that all of these things happen at the same time, okay? So there is parallelism that's happening. One thing that I've noticed that people have difficulty with is that in hardware, things are synchronous and parallel. In software, when we are writing things, we write one function and another function, and the functions don't happen simultaneously, right? So we are always having this sequential kind of execution of things. In hardware, that's not the case. Our controller our register file, our immediate generator, for example, all at the same time takes the same thing. And more importantly, for example, once the PC gets updated and goes through the instruction, also this value kind of gets updated, okay? So as you can see, once this value gets updated, this value also gets updated. At some point, this value is updated. It goes all the way here. We still don't know the control signal yet, so this value is not updated yet. So we need to wait for this signal to come in to make a decision, okay? So far, here we go. So all these things updated, the controller start decoding the instruction, takes the opcode, make a decision. We read two registers, so we get RS1 and RS2 here. We don't need immediate generator for an R-type instruction, right? But as you remember, I told you that, there is no way to kind of disable these units. These are combinational units. They work as they wish. So you still do this, but we generate some form of garbage here, okay? So that what we are generating here doesn't matter, okay? The moment that these values gets updated, hopefully the controller also gets the correct value. So at this point, this ALU source is equal to 0. So we select this and gets this. Then we have our ALU op is kind of generated, and our ALU control also gets the correct value. So our ALU now knows that it needs to do the R type. So we have add or subtract or add. We get this value here. We don't care about the 0. So 0 would be equal to 0. Branch also will be equal to 0. So at this point, we know that this is equal to 0. So it means that now this can propagate correctly forward. So again, things happen in parallel. So this thing happens while this thing also happens. At this point, we are looking at our controller signal, and this is the mem to reg kind of control signal, which should be equal to 0. So this value gets here. We go all the way back. We get to here. Here we have the reg write control signals. We have the destination register number. We have the destination data. We have the control signal. We update this register. We also have the next PC here. So we are good to go. Okay. So this is how it's going to happen for my R-type instruction. Of course, in this instruction, we don't use the memory. We don't need to use the immediate generator. We don't need to use this adder here. So some of the parts of my data path, although they're still switching and consuming power, they're not really doing anything useful for me. Okay? Any questions here? All right. So let's do the same thing for load. So again, things start from here. We go this way, we go this way, we wait here, we go this way, things happen in parallel. Here we need the immediate generator. By the way, this is a typo. This should have been 32. So we get our immediate generator while we also reading our register. One thing that you notice is that in load instruction, we don't have RS2, although we still put something here and we still we read the value here, but we read a garbage value here. But nothing bad happens because we use this controller signal to select the immediate instead of the register. So if we get this one, we get this one. ALU op in this case would be 0, 0. So in this case, ALU control, quickly say 0, 0, 1, 0 or something, whatever the number was, which was an add. 0 at this point would be equal to 0. Branch also 0. This value gets 0. This value propagates, goes here. At this point, since this is a load instruction, we use the data memory. So we put the address here. We wait for the data to come, and the data will come here. The mem to reg would now be equal to 1. So we select this one. We go down. We go back here, we put the data here, we put the address here, we put the reg write equal to 1 here, and that's how we update our load into our register file. Okay. There's also a whole bunch of things for store and others. In your homework, you will see that we ask you to kind of calculate the delays for this. So one thing that you will see in your homework is that we're going to ask you, for example, we're going to tell you that updating PC takes, let's say, for example, 20 nanoseconds. Reading from instruction memory takes 15 nanosecond. Reading from register takes 10 nanosecond, and so on and so forth. So for every single component, we're going to give you some numbers, and we're going to ask you how long does it take for a load instruction to finish. Essentially, what you need to calculate is following this path and adding these numbers together. One thing that you have to pay attention to is that some of these things are sequential, but some of these things are parallel. So for example, the controller and reading registers are parallel, but the ALU operation and the reading registers are sequential, right? Because for ALU to work, you need to get the data first from the register. So you have to wait for the register file to create your register. So some of these events are sequential, some of these events are in parallel. And the trick is understanding which one is depending on which one and how you compute the timeline, okay? So that's what we're going to ask you in the homework, and hopefully you can figure this out, okay? So some questions. Somebody asked, ALU up is 2 bits, right? Are we reading the MSB from this? So if you remember, ALU up was either 00, 01, or 10. 00 means add, 01 means sub, 10 means go and check 0.3 and 0.7. Okay, that's the rationale behind ALU up. Okay. Another question is, how is the timing from the memory managed? That is, how does the memory unit know when the memory is successfully read and returned? Nobody knows. That's why we have to calculate this time, okay? And say, for example, this whole time will be like 400 nanosecond, okay? I'm just making up numbers. So if this whole thing takes 400 nanosecond, if I give 400 nanosecond, I can guarantee that this process is successful, okay? If I clock and run the next instruction faster than 400 nanosecond, then I will not read the correct value from the memory, for example, and I get garbage, okay? So that's why calculating this delay is important for us to kind of decide how much time should be wait for all these things to happen, okay? Hopefully that answered the question, but there's no other way of knowing whether this value is returned or not. Someone says, can you please explain what 0 is used for in ALU on the diagram? Yes, so 0 is used for only for branch instructions, okay? So as you can see here, this 0 is this special flag, which is only is equal to 0 if RS1, RS2 is equal to 0. If this is the case, then 0 becomes 1. Otherwise, 0 is always equal to 0, okay? So why do we care? Because if 0 is equal to 0, then if the instruction is branch equal instruction, this is also equal to 0, and this one is equal to 0. So this AND gate would be equal to 0. And if you actually look into this kind of data path, you will see that what happens here is that if this is equal to 1, then we are selecting this path instead of this path. So we are selecting this path, and what is this path? This path is immediate plus PC. So PC plus immediate. Remember, we had the jump and we had to update the jump. So here we're going to get PC plus immediate. Otherwise, we get PC plus 4, okay? So this is for the jump instruction. If the condition for jump is true, then we need to jump, okay? How can we calculate delay? That's actually the question that we're going to ask you in the homework. We're going to give you the delays of each operation. That part, we're going to give it to you. The way that we're going to calculate that is just based on the delay of logic. So you don't have to be worried about that. So basically, for each operation that you're seeing here, we're going to give you a number. For example, we're going to tell you that adding takes, for example, 40 nanosecond. Okay, so in order to compute how long does it take for this wire to become valid, you have to say how long does it take for this value to become valid, how long does it take for this value to become valid, and then how much delay do I need to add for this value to become valid. Okay, so this is kind of the rationale that you're going to use for calculating the delays. Did I answer the question? For the jump instruction, someone asked, where do we store the current PC? Like, you mean by JALR, right? So remember that in this data path, we are not we're not using JAL or JALR. We are only supporting branch equal, okay? For branch equal, you don't need to save the PC. For JAL and JALR, you need to save the PC. Actually, this will be another question that we're going to ask you to change this data path so that now you can support JAL and JALR. And you will see that, for example, what you need to do is that you need to somehow move this PC to this right data register, because remember, you are saving PC +4 there. Okay, so that's kind of the idea here. But I'm going to let you guys to figure this out, because that would be one of your homeworks questions. Someone asked, the diagram is BEQ not LW? No, somebody asked about this and I answered them, but this diagram that I'm showing you is for LW. Someone asked that, will you holding office hours today? Yes, I will, but it will be on Zoom. Somebody asked, how do you ensure that non-valid values don't get operated upon? It seems possible that the control signals would be ready before the operands. So for example, maybe memory is up before the correct address is computed. Wouldn't the memory then read from a garbage address? It will, but remember that that's a great question. But for example, let's say actually what's going to happen here. Think about this as these are all combinational things, okay? So for example, if this value is equal to 1, before this address is a valid address, what will happen is this is a garbage address and memory is equal to 1. So we're going to read a garbage value. But at the moment that this value becomes valid, this value still is equal to 1, which means that at that moment, we're going to issue another load. And at that point, after some delays, we're going to get the correct value, okay? So as long as we calculate the delay correctly, the delay of this value becomes valid, this value becomes valid, and the propagation delay from here to here. If we let the processor enough time for all these things become valid, then it's guaranteed that this value becomes valid, this value becomes valid. Eventually, everything becomes valid. So yes, during the process, there might be garbage values, but eventually, if you give it enough time, things will settle down and settle to a particular number. That's why it's important for us to have enough delays. What if it were mem-write? Wouldn't there be a danger of writing garbage to the memory? No, because again, you're writing to the same thing over and over because of the address. And remember, one thing that will happen is if, for example, you're worried about that the address is garbage, but the value is not, we typically, when we are writing to the memory, we write it synchronously, okay? So while read or asynchronous are combinational, writes are usually, sequential, which means that when I want to write something to the memory, I don't write it during the clock period, I write it at the next positive edge of the clock, okay? So what will happen is that if the next, if the clock comes at this point, this is where my PC gets updated, okay, at this point. Then there will be some propagation delay for all of these things to reach to this point. This will be probably somewhere here, okay? So this amount of delay, okay? So all the values would be ready at this point. Things will not be written until this time, this next positive edge, okay? So as long as this time is enough for things to settle down, then we are good to go, because at the next positive edge of the clock, that's when we are writing things to the memory, or that's when we are writing things to the registers. So remember, writes are always sequential, which means that they're always synchronized with the clock to kind of avoid these kind of problems that you mentioned. Someone asked, is the office hours same as the class? Yes. And then let me see. Yeah, okay, I answered all the questions. Any other questions? Okay, somebody asked, when we talk about RISC-32, does it involve any scoreboarding or greater number of physical registers, or is it assuming only 32 actual physical registers? For now, we are only assuming there is actually 32, okay? So there's only 32. Later on, we're going to talk about having more than 32. But for now, we only have 32 registers, okay? Don't worry about more than that, okay? All right, so that's kind of it for this lecture. Hopefully you can kind of like follow this data path a little bit more, and then use the homework to kind of also go through different changes. We will ask you to make some changes to the data path, and you'll learn that. One final question is the reason that bit 30 was chosen as the only one that matters for func 7. Yes, because if you pay attention to this one, you'll see that really the difference in this set of instruction that we are using is this bit here, right? So the only thing that's really helpful is that func 7. That's 7 bits of func 7. The others are just garbage. If you had more instructions, then probably there will be other things, but in this case, only that 1 bit is enough. Okay? So, see, so we already did this. Okay, so that's it for this one. Let me go to the next slides, the new set of slides. Okay. So now that we kind of learn about, designing of the data path and the controller, let's actually think about how well this works. Did we do a good job of making as fast as possible design? Actually, how do we even measure how fast this data path is? How can we make it better, and so on and so forth? So now I want to take a step back and kind of analyze and kind of learn how do we measure performance? What are the important things when we are measuring performance? And then we're going to go back to that design that we had and see what we can do to improve it. So I basically, for now, just showed you the bare minimum you need in order to implement a processor. But of course, this is not what we're going to use in real world. There are lots of optimization that goes into this data path. So we're going to go through that. But in order to understand why we are doing those things, we need to understand what is important in order to measure the performance, okay? So I'm going to focus in this lecture on measuring that, all right? So this is kind of our design, and we call this a single cycle design, okay? As I said, the single cycle means that once a new instruction comes, okay? Once a new instruction comes, I'm going to wait until the values get updated. I'm going to calculate this delay, and I need to make sure that this delay, the clock cycle that I'm using, is bigger than this delay, okay? So the cycle should be bigger than this delay. Because if I do that, then I kind of make sure that nothing bad happens. Things are settled down, things are working great, and so on and so forth. And I'm going to keep doing this for every single instruction that I have in my data path and controller, okay? Very simple and easy, but it's not the most efficient. And now we're going to focus on why this is not the most efficient. And of course, the more important question is, what can we do in order to make this more efficient? So as I said, the important thing about designing the processor is this critical path. That is the different time, the time it takes for one instruction to go all the way and gets the results written either to the register file or to the memory or to the PC. Essentially, the instruction, the life cycle of an instruction starts with reading things from the PC and ends with either writing to the memory or writing to the register file. That's usually what happens for each instruction. So in order to make sure that all the instructions in my ISA is actually correctly executed, I need to make sure that the longest path, the longest time among all of these instructions is the time for my clock cycle, okay? Somebody asks, if the cycle is not close to the delay time, is there a risk of garbage value replacing the settled values? Yes. So if the cycle time is smaller than the maximum delay, then some of these units hasn't been settled yet, so you're going to read garbage at some point. So you're going to have correctness issues. So basically, what will happen is the longest delay determines the clock period, right? that's really the problem with a single cycle. Why the longest? The reason for the longest is in digital design, we always want to have exactly same clocks, okay? So the period of clock is not something dynamic. It's always the same. It's always 1 gigahertz, 2 gigahertz, 4 gigahertz, and so on. You cannot have one cycle that is 1 gigahertz and one cycle that is 2 gigahertz, because designing it is not possible in current digital logic that we have. So we always have a determined, a predeterministic, and fixed clock cycle, okay? For example, 1 gigahertz is 1 over 1 giga, which is 1 nanosecond, right? So it means that this period is 1 nanosecond. So my critical path has to be smaller than 1 nanosecond, okay? Or in order to decide how fast I can switch this processor, what is the fastest clock that I need to have, it basically the longest among all the instructions, the longest will determine the fastest that I can do, right? So that's really the rationale you're going to use for the clock. There's a question in terms of clock cycle you just mentioned. Does that mean you regularize every instruction so they all take the same time? No, they don't take the same time, but my clock cycle, it takes the same amount of time. So in reality, from the outside view, each instruction takes exactly 1 cycle. So in other words, no matter how fast each instruction finishes, in terms of performance, if I want to measure the performance of this, each instruction takes 1 nanosecond, okay? Why? Because my clock cycle is 1 nanosecond, right? How did I come up with this 1 nanosecond? This 1 nanosecond should be bigger than the slowest instruction in my ISA, because that's the one that's kind of like, that's the critical path. That's the one that decides the clock period, okay? So what is the critical path? Actually, if you solve the homework, you will see that the load instruction actually happens to be the slowest. The path for the load is the instruction memory to the register file, to the ALU, to the data memory, to the register file. And again, you will calculate the exact number, but you will see that the load is unfortunately the slowest instruction into my ISA. Okay, so we are kind of saying that my add instruction, okay, my add instruction, for example, could have finished in, let's say, 100 picosecond, but my load instruction needs 900 picosecond, okay? And what I'm telling you now is that everybody has to pay this penalty. So even though my add instruction could have finished in 100 picosecond, now I'm telling you that everything has to run at least for 900 picoseconds, okay? So I'm basically intentionally making my processor slower because I'm designing this as a single cycle design, because I'm telling you that things has to be, the clock cycle is fixed and the clock cycle is determined by the slowest. So even the faster one cannot really be that much faster, okay? So somebody asked, does the clock period change much when new CPUs or hardware are released, or are people wary of raising, lowering it since it affects every instruction? That's a great question. We're going to come back to the clock speed, but really what happens from one generation to another generation is that these delays get smaller, okay? So for example, when we have 10 nanometer technology versus 2 nanometer technology, the time it takes for the add to finish will be smaller, okay? So this path eventually gets smaller. As a result, I can clock things faster. So in reality, I can do faster clocks just because the delays get smaller. But what I want now is that I need to find some form of computer architecture trick that we don't pay this penalty for all the instructions. What I really want to do is being able to kind of like doing some form of adaptive method, so that some instruction takes faster maybe and some instruction takes smaller. Okay, so that's what I'm looking for in this design now. So that's the problem with single cycle, and that's why single cycle design is never actually used in real systems, because it's not a really efficient idea, because we are basically telling that your slowest instruction determines how fast your processor runs, and you don't like that, Okay, at the very least, you want your average instruction to tell you how fast you can run, right? So this is, by the way, this is by far it's the most inefficient way of doing these things. So the question is, can we do better? And let's wait and see if anybody has any suggestions. So anyone wants to chime in and say, what do you think we should do in order to make things faster? Either unmute yourself or just put it in the chat. Someone says prefetch instructions. So prefetching instruction wouldn't help us that much with. So remember, what I want to do is that I want to make sure that one single instruction can be executing faster. What can I do in order to make that? Someone says parallelize instruction execution to the best of our abilities. Yeah, that's closer to what I'm looking for. So we need to somehow, like, do some trick to make these things faster. So let's see actually how. So again, recall that what we're really looking for is making efficient or fast computers, right? So the question that we are looking for is making things as fast as possible. Somebody also says caches, so they're trying to kind of reduce the delay of memory, and that's a good way to make things faster. But remember, we want to make everything faster at the same time, not just one particular instruction. But that's a good strategy as well. Okay, somebody says multi-cycle design. So the idea of multi-cycle is that I'm telling you that, you know what, I need one clock cycle to finish things, and this clock cycle is determined by my slowest. So what can I do in order to make things faster? It's saying that, okay, maybe for every single, instead of like saying that, okay, every single instruction has to take one cycle, maybe I say load takes 4 cycle, but add takes 1 cycle, okay? So if I know beforehand which one is which, I can maybe give more time for the load to finish, okay? That's something we can do, and multi-cycle is actually something that people come up with after single cycle, but unfortunately, multi-cycle has its own problems because makes the design very, very complicated, and it doesn't really give you that significant boost. So the answer is actually yes. Somebody says pipelining, and we're going to actually talk about pipelining at the end of this lecture. The answer to this is what we're going to do, and that's kind of parallelizing things and make things kind of decouple from each other to make the fastest possible. So for now, let's put that into the bed. But let's focus on this fact that what is efficient? So what are we trying to achieve? And then I'm going to later, if you have time, we're going to talk about how do we actually achieve that, all right? So let me give you a few metrics, first of all, to kind of knowing that what is the way of measuring efficiency. There are two things that computer architecture and computer architects in general really like. And one is latency and the other one throughput. The latency definition is how long does it take for a task to finish, okay? We usually measure latency in terms of time, like second and milliseconds and microseconds and so on. For latency, of course, lower is better, right? The lower the latency, the faster that it can do. So when we are designing a processor, what we really, really want to do is that the latency per instruction we want to remove, reduce this, right? If I can run instruction faster, then my overall execution time will go better. Excuse me. Another important metric to remember is throughput, okay? The throughput is slightly different than latency, and the throughput definition is how many tasks can I do for a given time, okay? And this is usually a ratio. So it's typically, say, for example, instruction per cycle or bit per second, and so on and so forth. Unlike latency, throughput is higher, it's better. So what is happening with single cycle design is that my throughput for single cycle design is essentially 1. I can only do 1 instruction per cycle, okay? And that's the biggest problem with single cycle. What we will see is that when we are designing the pipeline, we're going to make this throughput significantly faster, usually 5 times faster, okay? And of course, we want to do some tricks to make this latency also smaller. So for example, people talk about caching and new technology and so on. So in short, if I want to make things faster, I need to reduce my latency. I need to improve my throughput. So these are the two things I'm going to look after. And when I'm talking about pipelining, I'm going to show you how we are actually making both of these things to work and how we make things better in both cases. There's also 2 other metrics that you kind of need to be aware of, and that is power and energy. Power is measured by joule by second, and of course, lower is better. And energy is the kind of the product of power and latency, okay? So if you add more things to your processor, your power goes up and your latency goes down. But the interesting question is, what will happen to your energy? Does your energy goes up or down? And that's where you kind of like all these decisions that we make in the processor eventually comes down to this energy question as well. Of course, if the energy is an important metric for us, for example, for a large CPU or a server, maybe the energy is not the biggest question, and maybe the latency is the big question. But in many, many systems, energy is kind of the deciding factor because it's a function of both the power and latency. So if you add something that's kind of significantly reduce your energy, but significantly increase your power, maybe that's not a good decision to make because that creates a much more energy consumption. So these are the trade-offs as a designer that you need to pay attention to. All right. So one thing that I always get like the question that people are very confused is that is throughput is basically 1 over latency. Are these things interchangeable? Okay. So for example, to give you 2 examples, for example, if it takes t second to do 1 task, then by definition, latency is t, okay? Can we say that the throughput is equal to 1 over t? Because if I say 1 task, t second, so latency is t, so can I say the throughput is 1 over t? Or in other words, if it takes t seconds to do n tasks, my throughput by definition would be n over t, right? Can we say that my latency is t over n or not? So these are 2 important questions. And in general, the question is throughput and latency are the same thing? It's just the inverse of them. And I want to know if anybody wants to say yes or no. How many of you think it's a yes? Maybe someone wants to volunteer and say why they think it's no, they're not the same thing. And if that's the case, why do you think it's not the same thing? Let me create a poll. Yes, no. They. All right. Put it in the I put it in the chat. Do you think it's the same thing or not? All right, so we have like people still putting in, but we have around 80% saying no and around 20% saying yes. So the answer to this is it depends. In most cases, it's not, but in some cases, there is. The reason that these things may not be the same is there might be some form of concurrency. Actually, someone said it in the chat as well, that if there is concurrency, then the throughput and latency is not the same thing. So I'm kind of showing you a graph here that, for example, let's say we have 3 different tasks, T1, task 1, task 2, and task 3, okay? And in this case, as you can see, the time it takes for these tasks to finish is T, right? So the latency for finishing these 3 tasks together is T. But if you actually added the individual latency of each one, then you would have got much bigger number, okay? So in this case, I finished 3 tasks in time 3. So my throughput is, the number of tasks 3 over T, but the latency of each individual task is not 3 over T over 3, okay? The latency of them, in fact, is actually much longer. The reason that I managed to finish this much faster is because I managed to do this concurrently, okay? So individual tasks, it still takes a lot of time, but I managed to kind of parallelize these tasks. So the whole time takes much faster, like, whole times is much faster. And my throughput, in other words, is faster and more. So it's something to remember that throughput and latency are not necessarily the same thing. If there is no concurrency, if everything are strictly sequential, then of course they are interchangeable. But if there is concurrency, then throughput and latency is not the same thing, okay? So let's continue. Another thing that I want to tell you is there is some form of confusing terminology that I'm going to use. So I want to also clarify that. And that is when I say something has been improved by 2.5x, in other words, it means that it has been improved by 150% or improved by 2.5 times, okay? So that's something to remember. Another thing is when I say improve, that depends on the metric. So for bigger is better metrics, improve means increase. But for smaller, better metrics, improve means decrease. So when I say latency has been improved, it means that it's actually now takes less time. If I say throughput has been improved, it means that it actually takes more, that the absolute value has been increased. So just pay attention to this terminology that people use in computer architecture, okay? So let's go back to kind of like the performance measure. Remember, I want to design a new processor, okay? And I want to make this processor faster. Before jumping into the faster part, we need to understand what is faster and what we want to do. And what we have learned is latency and throughput are the 2 things that kind of help us to make the processor faster. And as I said, if there is some form of concurrency, then they are not the same thing. So you can actually try to tackle both. If there is no concurrency, then they're basically the same thing, okay? So how do we measure the overall performance of our processor? Basically, we're going to use the time, the overall time as the measure for performance, okay? So what we are saying is that yes, individual task and all those things, that's okay. But if the end-to-end latency, if I have like n task, and if I just look at it as a black box, that I put the input, I wait, and I see the output, what I'm going to do is I'm going to measure this time. And I'm going to say that computer A versus computer B, I'm going to tell computer A, for example, is faster if the time it takes for finishing the set of tasks for A is less than the time it takes for set of tasks in B. Like very straightforward. So time is really the measure for measuring how fast a computer is, okay? For the same amount of work, for the exact same workload. If one computer can do it, can finish it faster, we call that a faster computer, okay? And now the question becomes, how do I measure time? And you might think that, measuring time is something trivial, but in fact, it's not. The reason that it's not is because we have a bunch of different things, okay, going on at the same time for a program. So let me kind of break down this figure for you. So we have this measure time, what we call elapsed time or wall clock time. This is the time that we can observe from an external part of a computer. In reality, though, This time is combination of bunch of different things at the same time. It's combination of time it takes for running system activities. It's times that it takes to run program A. It's time it takes to run program B, and so on and so forth. Somebody asked, can you re-explain what CACB and TATB represents? Yes. Where were we? This is computer A, computer B. So what I mean is that if I have two computers, A and B, and if I have a program that I run on these two computers, okay, I put this here, I put this here, and now I measure time. This is TA and this is TB. What I will say is that this computer, for example, A, is faster if the time it takes for finishing the same task for computer A is less than the time it takes for this computer. Okay, so kind of like very straightforward thing. But how do I measure this time? The measuring this time is not that straightforward, because as I'm showing here, the time that we are observing externally, that TA that I said or TB that I mentioned, this is actually a combination of multiple different things. It's combination of some system level activity, because when you're running a program, you have to first load it, and then it has to first kind of communicate with the operating system. There are a bunch of system calls and so on and so forth. Then there is, like, other programs also being running. There might be context switch and all those things. And even within the systems or within the program, there is IO activity and there is computing activity. So there is time that you are kind of running instructions, and there is time that you're waiting for your input output to kind of read something from the memory or from the pins or from the output and so on and so forth. So there is kind of different things that we are really measuring. When we are talking about the time it takes for a program to run, what we really mean is this time, okay? We usually call this CPU time, okay? This is the time that it takes for the CPU to run this program, okay? The problem, though, that the time that we can measure outside the system is this wall clock time, okay? Which is combination of a bunch of different other garbage that is added to this compute time. So what we're having here is much, much larger than this compute time, unfortunately. Okay, so we have to be very, very careful about the difference between these two and the way that we measure this. Okay, so it's very easy to measure this, because this is something that you can literally use a timer. Just boom, run a program, wait for it to finish, and that's the time that you can measure. But this is really not that simple to measure, because this is the internal part of your system. And you can really don't have access to this, okay? What is important for us when we want to improve the design of the processor, what we really care about is improving the CPU time. We don't care about the IO, we don't care about the system and all those other things. These are questions for other courses that you're going to have. So 111L, for example, talks a lot about this part of the system. But as a computer architect, what we really want to do is being able to make this CPU time here as small as possible. So this would be our kind of goal. But in reality, this is a combination of a bunch of other things in order to get the final latency, okay? So I wanted to kind of distinguish these things from each other so that you see that this is what we are focusing versus this is how we're measuring this, okay? Of course, you may want to know, how do we measure this if you only can measure this, right? And the other things that you want to ask is the CPU time some form of like average behavior? Is it for a particular program? What will happen if we change the program to some other things, and so on and so forth? So these are the two questions that we need to answer before I jump into how do we actually improve the CPU time. Before that, let's have a quick 5-minute break. Let's come back at 1:10, and then we can talk about this, okay? All right, let's continue. So 2 questions. How do we measure CPU time if we only can measure wall clock time? And the second question is, what type of application should I use to even measure CPU time? Because one thing that you may be wondering is different applications might have different CPU times. So which one are you actually going to report? The first question is, you can measure CPU time by some tricks that we have. We run the program, we measure the time, we average it over many, many runs, or we kind of disable some form of activities that we do on the operating system, or even we do kind of benchmark all of these different activities in order to find the CPU time. The problem with that is usually too costly. The reason for this is that you need to build the actual hardware, you need to run this on a real hardware to actually get the results. And sometimes, for example, in order to know whether just one particular kind of change in your CPU design results in a faster computation or not, building the entire thing is not the best thing to do. So what people usually do is using some form of simulation. Basically, the idea here is that you kind of like mimic the behavior of the hardware, kind of create some form of simulated behavior of the hardware. And this way you can actually measure the delays and the interaction and so on and so forth. And this is actually something that's very, very commonly used in computer architectures. Hardware simulators is something that people love to do because building the actual hardware is very, very costly, and you don't want to do that. So, but writing a piece of software that mimics the behavior of the hardware is actually pretty simple. So that's what people do in order to kind of measure the impact of the change that you make in the hardware. In fact, that's what we're going to do in your project as well. We're gonna ask you to build a very simple RISC-V processor in C++ that kind of mimics the behavior of an actual hardware implementation of the same thing. So then you're going to kind of see the difference between these two. You're going to see the behavior of your code, and that's basically what an actual hardware would have done. And this makes things much faster in terms of the cost and design and so on and so forth. Someone asked, does the processor simulator always simulates an entire system along with it, like how Gem5 functions? Yes. So Gem5, by the way, for those of you who don't know, is a very famous microarchitectural simulator, but there's a whole bunch of other simulators that people use. Gem5 does what we call system simulation, which basically simulates this entire thing. So it doesn't just simulate this, but it also simulates this and also simulate this and this and this, okay? So we call this a full system simulations. But there are also simulators that just simulates this. It doesn't care about these other things, okay? So the granularity of the simulators really depends on what you're going to design. For example, in your project, you're just basically focusing on this, but in like high-end simulators, other people can do other things as well, okay? And then the second question is, how do we actually pick the applications? We do this trick called benchmarking, okay? So the idea is that different applications has different characteristics. So it's not fair nor accurate to just focus on one single application to tell whether your processor is becoming faster or not. What you would do is what we call benchmarking, which you use a collection of programs that are very carefully designed to measure a specific metric. For example, if you want to see if your CPU time is going up and down or down, you pick a collection of applications, let's say 10 to 20 applications, and run all of these together, like one by one or all together or whatever, and then measure the CPU time of all of these, and then average them and then report that. If on average things gets faster, you can now claim that your new design is faster. If you're on average, your system gets slower, then you can say that, you know, whatever change that you made didn't really help in making the system faster. Okay. So benchmarking is not something that everybody does. Usually there are, you know, companies and researchers who spend a significant amount of time of carefully designing this. The reason that you want to carefully design this is you want to kind of make sure that your applications are as diverse as possible. It's really using all part of the processor, including the interaction with I/O or memory or different components within the processor and so on and so forth. So when we are designing our benchmarks, it's not like something trivial that we do. Okay, you probably have heard about spec benchmarks. Spec. This is the most famous. Spec. This is the most famous benchmark that we use. If you actually pay attention to when like a new Apple, processor comes out, like M2 or I don't know, Bionic 14 or whatever. If you like, look into the YouTube videos and so on, you see that someone is running spec and say that on spec, for example, we see an improvement of, I don't know, 3% or whatever. This is exactly what is happening. That spec is this list of applications, standard applications that everybody can use. They run it on the processor and see how fast it can run this. And then when they see it, and then they report the average, they say that, okay, the processor is this much faster or so on and so forth, okay? And the purpose of benchmarking is different from different people. The architects wants to show that their hardware is better. The marketing wants to, kind of like, bank on this fact that, I don't know, the newer generation of the processor is really faster and so on. And of course, for the end user, this is kind of one metric for you to decide which processor to buy, right? So when you're deciding whether I want a new laptop or not, or whether I should buy this model or that model, if you care about your performance, that's probably one thing that you're going to use. You're going to use the benchmarks or look into the documents for the benchmarks to make a decision. In fact, you can actually, next time that you're buying a new laptop, go and kind of like Google, like, the performance results of the processor of your laptop to kind of get some idea. Anyway, so what we wanted to say is we need to care about some metrics. Time and throughput is the two important metrics that we care about. And then we talked about how do we measure this metric, and we said that essentially what we are really caring about is the CPU time, the amount it takes to run a bunch of different programs on the CPU and the time it takes for this to finish. That's what we're going to focus, okay? So based on this, I'm gonna introduce this what we call this iron law of the performance of the processor performance. So the iron law of processor performance basically says that the CPU time is a function of three things. Okay, it's function of instruction count, cycle per instruction, and cycle time. Okay, so I'm going to break down what each one is this, or like, explain each of these one by one. But generally what this formula tells you is that in order for you to make your processor faster, and that would be our blueprint in the rest of this class, is either I need to reduce the instruction count, either I need to reduce the cycle per instruction, or I need to reduce the cycle time. Or of course, I can do all of these three at the same time, or two of them at the same time. And that's what we're going to do. So all of these decisions that we are making from now on is based on this basically iron law that I want to, impact in one of these three categories. Okay, so let's jump into the description of each one and see what happens. So first of all, instruction count, we usually show it as IC, and instruction count is the number of instructions that we're going to execute. In other words, how large is our program? So for example, if you're running a very large program with 100 instructions versus another program with 1,000 instructions, if everything stays the same, I'm expecting that the CPU time for this for this program is 10 times more than this, right? This is kind of straightforward. If I need to run more instructions, the time it takes for running those instructions is more, okay? So important things about this is that in order to reduce this parameter, I need to decrease this IC. How do I do that? There are two things that we can do in order to reduce this IC. The first thing is IC is basically a function of your algorithm, okay? If, for example, you're doing sorting, okay, if your sorting is very complex, then you definitely need more instructions, right? So it means that your general CPU time will be higher. So if you manage to use a more clever algorithm, for example, for sorting or for whatever else that you want to do, then your instruction, the number of instructions reduces, and as a result, your CPU time reduces, okay? So whatever you do at the higher level, at the software level, or even at the algorithm level for writing your programs, that directly impacts your CPU time. Less instruction means faster execution, right? Another thing that is important for IC is use of better compiler, because compilers are the ones that translate the higher level language like C and C++ to some form of assembly, right? So if this compiler does a better job of reducing this number of instructions, then this IC goes down and this CPU time goes down, okay? So that's the story of designing a better compiler, and again, separate class that you probably have taken or will take sometime in the future when we are talking about programming compilers. Same story for programming languages, and that's why it's important for us to design a better programming languages, because reducing instruction count will reduce the CPU time. Someone asked, would using a sys architecture reduce instruction count? Yes, exactly, will reduce instruction count, and that's one of the benefits of using CISC. But we actually gonna, at some point, we're gonna compare CISC and RISC, and you will see that while CISC reduced the instruction count, unfortunately, it increased the cycle time, and the results, it may not be beneficial. So you have to be careful about the impact that whatever you do has on all three. So for example, if you do something that reduces but increase these two, the overall time might be actually higher. So it might not be useful to do that. But yes, CISC will reduce instruction count for sure. The second thing is cycle per instruction, or we call it CPI. Another thing that is widely used is IPC, or instruction per cycle. IPC is 1 over CPI, okay? If cycle per instruction is, for example, 5, it means that it takes 5 cycles for finishing an instruction. Your IPC is 1 over 5. It means that per cycle, you just run 1/5 instructions, right? Another metric that we use is MIPS. MIPS is million instructions per second, again, similar to IPC, but generally the idea of cycle per instruction is how much time do I spend per instruction, right? So what you want to do is you want to reduce this CPI, okay? So you want to reduce the CPI, and you want to design your processor such that, you know, the cycle per instruction is as less as possible. For example, what you will see is that for some instruction, your CPI might be more than some other instructions. For now, we are designing single cycle. For single cycle, everything is just equal to 1. But later on, you will see that we're going to design other, you know, methods. And there you're going to see that, for example, some instructions takes more cycles than the other instructions. So we need to kind of like figure out some ways of improving this, okay? We're going to talk a lot about this cycle per instruction. Actually, the most things that we're going to talk about in this course is about the CPI. So we're going to come back to CPI a lot in this course. Somebody asked, so in each variable in this equation, so is each variable in this equation inversely related? One goes down, the rest goes up. Not necessarily. So for example, if you look at the algorithm, if I use a better algorithm to reduce the IC, the other two won't be impacted. So they stay the same, but just the IC goes down. In some other cases, they might be inversely related. So yes, for some, you know, optimizations, but no for some other optimizations. And of course, if everything was inversely related, then there won't be any optimization in the CPU time. But in fact, there are lots of things that we can do in order to improve CPU time, okay? And the last thing to talk about is cycle time. So cycle time is essentially 1 over the frequency of the clock. And generally, the main thing to remember about the cycle time is if I have a faster clock, then I can reduce this, okay? So if I can somehow manage to kind of like run things faster, then of course I reduce the cycle time and I reduce the CPU time, okay? And an important thing is about CT or cycle time is device level and architectural level improvement is that place that kind of improves it. So remember I told you that, we moved from a non-MOSFET technology to MOSFET, or we started from higher size of transistor to lower size of transistors. The impact was exactly this, that smaller and smaller generation help us to make things faster. In other words, makes the cycle time smaller. Somebody asked, so generally IC and CPI are inversely correlated. Again, not necessarily, right? So CPI is decided by the way that your microarchitecture works, okay? So if you can somehow make things faster, then you can reduce your cycle per instruction, but your instruction count stays the same, because instruction count is only based on the program that you're going to use, okay? But of course, if you, like, for example, use something like CISC, CISC, what happens is that you're saying that, okay, I'm going to morph these instructions together. So I'm not changing the algorithm. I'm just changing the way that I map this algorithm to the program differently. So I'm going to reduce this. But by doing that, unfortunately, I'm going to increase this because I make my processor more complex. So apparently, possibly it's going to be more cycles required to run that instructions. Again, there won't be always a correlation between the 2 or 3 of these. Some of them are independent from each other and some of them are not, okay? Okay, so this is the last thing. And again, one more time, going back to this, our iron law is CPU time is equal to instruction count times CPI times CT, okay? And we want to talk about how to improve this. This one, and this one, there's not much you can do at the macro architectural level, because this is mostly depending on your algorithm or your compiler, and this is mostly depends on the technology. But this one we're going to play a lot with, actually kind of combination of this one and a little bit of cycle time. So you're going to see a lot of things that are going to happen, and all these technology and features that we're going to add to our processor. Really what it's going to do at the end of the day is decreasing this and eventually decreasing the CPU time, okay? So now that we know all these metrics, let's actually talk about the things that I wanted to talk. And that was the problem that we had with single cycle to the thing that we're going to use, which is called pipeline, okay? So let me explain what this pipelining is, and then explain how does this going to help us. And next lecture, next week, we're gonna dive into the microarchitecture of the pipelining as well. Excuse me. Before that, as I said, you can also have, instead of having only either one single cycle or pipelining, we can have a kind of a middle ground, which is the multi-cycle or multi-stage. The idea here is I can actually have like multiple stages in my program, in my data path, and then say that, okay, each stage takes one cycle. And depending on who is going to use which stage, we're going to have multiple cycles per instruction, okay? And this way, of course, I'm going to break down the critical path because, for example, my add only takes 3 stages. It doesn't need the memory, so I can skip this. But my memory takes, for example, 4 cycles because it needs the memory. And this way, I'm kind of saving 1 cycle for add instruction. So compared to a single cycle, this is slightly faster. The problem with multi-cycle is that kind of the skipping is not the most efficient thing to do because there are lots of things I need to add to my data path and controller to kind of decide what to do and what not to do and when to skip and when not to skip and so on and so forth. That in reality, this multi-cycle approach is really not much better than single cycle because although I'm kind of increasing this like I'm kind of reducing this, I'm really not helping with cycle per instruction because things becomes more complicated. So I'm really not going to talk about multi-cycle at all in this class because it's not something that anybody is using anymore. Instead, what we are doing is we are kind of using what we call a pipeline stage or multi-stage pipelining, okay? The way that we're going to do this is, for now, let's go back to the design that we had and showed you before. We're going to kind of have a logical, combination, like logical dividing of the pipeline into what we call 5 stages. We call this a fetch stage, we call this a decode stage, we call this execution stage, we call this memory stage, and we call this write back stage. For now, just ignore why we are doing it this way and why I'm calling this. Just for now, just assume that for some reason that I'm going to explain later, I want to partition this design into multiple stages or multiple cycles, okay? So one thing that you have to pay attention to is when we are doing this, what we can do in order to kind of make this multi-stage is that in order to kind of decouple these stages from each other, we can actually add registers here, okay? So each of these dotted lines could be a register that what will happen is that instead of saying that, okay, for each instruction to finish, I need to start from here, go all the way, and wait for this to settle down. All I need to do now is basically doing this thing where I'm going to say that all I need is for each stage, I need to wait for this value to settle down, 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 and this value to settle down, okay? So I'm breaking down my critical path into, for this particular case, 5 different parts. And now I'm basically saying that in order for me to go to the next stage of my clock, all I need to do is waiting for these individual states to settle down, okay? So instead of like, so eventually I'm hoping to get 5 times faster clock speed because now I can run things much faster because I don't need to wait all the way. I just need to one small event to finish so that I can store things. So I'm basically adding this register here and registers here. So basically all these wires are going to be registered, okay? So we're gonna store everything here and register everything here to kind of remember this and decouple them from each other, okay? So this is the idea I'm going to pursue. And of course, this is going to be what we call states, okay? So kind of like what is really happening here is that I'm going to have some state elements, some register. I'm going to have some combinational logic, and I'm going to have some other state, okay? So for example, in this case, as you can see here, I'm going to have this register here. PC is a register. Then this is my combinational logic. This is the same as before. And instead of having another combinational logic and another combinational logic and another combinational logic and so on and so forth, which the delays will add up, I'm going to break this down into multiple states, okay? So I'm going to say that I'm going to add a register here, okay? So I have my combinational logic here. Now I'm going to add a register here, okay? So the time it takes for this combinational logic is now this one, because now the next positive edge of the clock comes, and this value will be stored into this register. And then I have another combinational logic here. And again, this value will be updated the next time that this combinational logic goes, and so forth and so on and so forth, okay? So I'm going to have a state. This is my register, okay? This is at the positive edge of the clock. This value will get updated. Now the times for the entire cycle, clock cycle, would be the time for this combinational logic to propagate and settle at this point. And now I add another register that once this positive edge comes, this will stored here, okay? So I'm breaking down my critical path of combinational logic to a smaller path, and the cost that I'm paying for this is adding this extra pipeline registers or in the overall registers, okay? And somebody asked, are these registers separate from that 32-bit registers? Yes, these are not general purpose registers. These are just registers that I'm adding to my data path to kind of break down my combinational logic into smaller pieces, okay? So now things are kind of like moving. Think about this as kind of like a pipeline of like building things. So you kind of like assemble something, put it to the next stage, assemble something, put it to the next stage, and so on and so forth. So somebody asking, how does adding this registers help? Or somebody wants me to explain this. In a minute, I'm going to explain why this will help. But for now, let's see what I'm going to do. So let me explain it one more time. So without this registers, what I had was, this was my delay, right? So it started from here, I have to go here, and then here, then here, 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 here. And I told you my clock cycle, right, has to be bigger than the whole delay of the entire thing, okay? So I want to fix that. So here's my proposal. My proposal is that I'm going to break down this combinational logic into pieces, okay? What I'm going to do is I'm going to add these registers here, this kind of dotted lines here. So what will happen with this is that now my delay is the time it takes from here to here, okay? Because this is the next positive edge of the clock. Now the next positive edge of the clock, the data is updated here, it propagates through here and stops here. So the time it takes for me for next clock is just this one. And then the time it takes for the next stop is this one, and this one, and this one. So now if you think about how fast can I clock this design, okay, you will see that the fastest that I can design this is basically the delay. Let me go back here. Sorry, the fastest that I can clock this is the largest delay between these. Okay, so for example, if this is T1, this is T2, this is T3, this is T4, and this is T5. Now I can much faster, change my clock, because remember, previously my clock has to be bigger than T1, T2, T3, T4, and T5, right? Now what I'm telling you is that your clock is basically has to be bigger than max of T1, T2, T3, and T4, and T5, okay? Why? Because I'm decoupling the time it takes for this one to go propagate all the way through and coming back, because all I need to do for things to settle is that now I need to just things from here to here to settle. Now I only need from things to settle from here to here, and same for here, same for here, same for here. So I'm basically saying that I can now run my clock much, much faster because I'm adding this kind of intermediate registers, okay? And again, for now, don't worry about why we are doing 5 and why I'm putting it here. I'm going to explain that later to you. But for now, just assume that we are adding 5 pipelines, basically these 4 and this PC here, to kind of make this what we call a 5-stage pipeline design, okay? So let's see if there are any questions. So how does adding register help? So I think hopefully I answered these questions, that adding the register helps, makes this clock much faster. So going back to the iron law, I make CT significantly lower. And I'm going to later on talk about what will happen to CPI. But for now, just assume that CT goes much, much lower. So this makes the overall CPU time much faster. Okay, that's one benefit of doing this. Somebody said, if anyone is interested in a real-world example, try this approach with their last single score to crank up, but the result was that they were outperformed by their Pentium 2 predecessor despite the double the clock speed. That's actually not true, and I'm gonna come back to that, but just hold that thought for a second. So somebody asked, so does it turn into 4 super short clock period to complete one instruction instead of one long period? Exactly. So actually 5, right? So this is 1, this is 2, this is 3, this is 4, and this is back to the register 5. So we are basically breaking down one really long clock cycle to 5 shorter clock cycles. Okay, that's what we are really trading off here. Somebody asked, is it possible to transition from one state to another in one or multiple of a cycle, or do delays still cause computation to not be fully lined up with the clock? Because the diagram showing the state doesn't seem to line up with the clock. So as I said, your clock still has to be designed such that it's bigger than the maximum between them, okay? The reason that it's maximum because not necessarily all of them takes the exact same time. So this one might be longer than this one. So I need to make sure that among these 5 different stages, my clock is slower than the slowest, okay? So that's what we're going to get from this design. Does this mean that the cycle per instruction enhanced while time per cycle is smaller? In fact, cycle per instruction won't enhance, and I'm going to get back to this in a bit. But for now, what's really changing is that my clock speed would be significantly faster, okay? On average, I'm hoping to get 5 times faster. In reality, it won't be exactly 5, but it would be very close to 5. So somebody asked that, so we are adding a register at each blue region. Yes, so this is the registers that I'm adding, okay? So we are adding lots of registers. So every single line here, there is a specific register, okay? So somebody asked, wouldn't the cycle per instruction go up 5x? That's actually a great observation, and I'm going to come back to that. The short answer to that is yes. Also, is it one register or multiple? As I said, these are multiple registers, okay? These are lots of registers here. But somebody said, but even with the breakdown still dependent on the previous stage time, right? So as you can see here, what is happening is that my clock time is now much faster, right? So in the past, my clock time was T1 plus T2 plus T3 plus T4 plus T5. But what I'm showing you here now is that since I'm decoupling this part from this part, now my clock speed is maximum of those, which is in fact about 1/5 times faster, okay? How are we breaking down the cycle? Does the register serve to save the previous state so that the next run can be simulated? So yeah, again, so when I'm adding this, I'm storing whatever happens here. So now that we are decoupling what is happening on this side and what is happening on this side, right? There's a register that remembers what happens. So there is a independency between this part and this part. That's how the register will help us to make these things work. Somebody says, intuitively, introducing register will introduce more propagation delays. How does this help the CT? So it helps CT this way, okay? The reason that we are breaking down this into this, that's how it helps CT. What you're saying is that this register itself adds some tiny bit of delay. And in fact, that's an important observation. But for now, let's assume that there is no delay added by these registers, okay? Registers are instantaneous. Just for now, assume that. In that case, then breaking this down will help us to significantly increase the clock time, okay? Somebody says intuitively introducing registers would introduce, oh, okay, so I answered this. If we split the cycle into 5 smaller cycles, but it's still limited by the overall bottleneck, how does this actually increase performance? Don't instructions still have to pay the bottleneck penalty at each stage? No, because now I'm breaking down the bottleneck from the entire thing to just one stage. Basically now, remember the last time the bottleneck was, I'm adding these 5 and that was determining my clock. Now I'm telling you what is determining the clock is whichever of these states are the slowest. Okay, that's how I'm actually like shifting that bottleneck from the full end-to-end delay to per stage delay. Okay, and can you explain the effect of CPIs? Let me actually just move forward so that I can answer these questions, because once I explain this, you will understand how this actually impacts the rest of the things. Okay, so let me actually tell you how many are we adding and where we are adding the stages, and why we are adding those. So the reason that we want to add this, as I said, is that we want to kind of hopefully break down the CT into equal parts. Okay, so the kind of intuitive design here is that we want to make these stages as equal as possible, because if we do that, then our CT is basically divided by n. If I adding n stages, it will be divided by n. Okay, so the reason that I'm putting these here is for that. There is another thing that kind of determines the number and why we're not really adding even more, and I'm going to explain that later. But for now, the reason that we're kind of putting these things here and maybe not putting it here or not putting it here is that I want to make these stages as balanced as possible. So hopefully all of them takes this exact same amount of time. Okay. So this is kind of the simplified version of what I'm showing. So I put my instruction memory here, I put my register file here, I put my ALU here, my my data memory here, and my register file right back here. Okay. So let's see actually what is happening here, because there are lots of questions on, oh, what happens to cycle time? Oh, what happens to the CPI? So let's talk about these. Okay. So let's go back to our iron law. And remember that it was a combination of IC, CPI, and CT. So let's see what happens to each individual one of these. So first of all, as I said, my cycle time will reduce, okay? Remember, my cycle time previously was T1, T2, assuming that I'm doing 5-stage pipeline, okay? It was this, okay? And now what I'm telling you is that it will be now this, okay? And I'm telling you that the way that I'm going to do this pipeline is that roughly, very roughly, not exactly, but roughly, this is what I'm going to get. Okay, so I want to design my pipeline such that these 5 times are almost the same. In that case, the max of this would be 1/5 of, if this is equal to t, this would be 1/5 of t, because if they're exactly the same, we're going to do this. Okay, so my cycle time would reduce, okay, by a factor of 1/5. But one thing that won't reduce is CPI. So what will happen to the CPI is that my cycle per instruction now is actually 1/5, because what is really happening here is that the same instruction has to go to 5 cycles. So my CPI is actually 5. The number of cycles per instruction is 5, because it takes 5 cycles for one instruction to finish. My CT is 1/5, but my CPI is 5. And actually, if you look at the CPU time, my CPU time stays the same, because yes, I decrease CT, but I increase CPI, unfortunately, because now it takes 5 cycles to finish this instruction. So my CPU time didn't really change, okay? And that's the problem that we're going to face with pipelining. And now that, of course, the question is, can we do better? And that's the story that we're going to tell you next time that we're talking about this. Before letting you go, let me actually go to this participation. Let me share with you the code for today. And then, of course, I'll be here for you to answer questions, okay? So don't worry. If you want to stick around. 6, E, F8. It should be active. Okay, so this is your code, and let's actually answer some questions. Okay. Okay. So we are adding registers.
Also, one register multiple, I answer that. How are we breaking down the cycle? Does the register save to save the previous states? I answer this. Answer this. Yeah, so somebody say, I think eventually going to get multiple instructions can be done at the same time. Yes, that's what we're going to get from the pipeline. But what I'm showing you so far is essentially what I'm doing. So what I had before was, this was my design of the CPU. The CT was combination of 5 different times, okay? But now I'm saying that, okay, let's break this down into 5 stages. And this is T, okay? So what is happening now is my CT my CT2 is 5 times of CT1. So great, CT going down. But the problem is instruction still takes 1 cycle, 2 cycles, 3 cycles, 4 cycles, and 5 cycles. So my CPI2 is also 5 times of CT1. Sorry, CPI2. CPI1. Sorry, this is 1/5. So I managed to decrease CT, but unfortunately, as a result, I'm increasing my CPI, and these two kind of cancel each other out. So really, I'm not getting any benefit so far, okay? So I need to do something else, and I'm going to explain what that something else is next time we are talking about this, okay? So hopefully that can answer lots of questions. Somebody asked what would happen if that the memory read is feeding register from 2 cycles after. How does that happen? Don't worry about the implementation of the pipeline. I'm going to explain that to you next time, okay? So somebody asked why CPI is equal to 5. The CPI is equal to 5 because now it takes 5 cycles for one instruction to finish, because it has to start from the first, then go to the next, and next, and next, and next. So it takes 5 cycles per instruction to finish this activity. So that's why CPI is equal to 5. Okay? 6 or B, this is 6. Working. Yeah, this is why. Sorry for my bad handwriting. So somebody asked, how can we just look at one stage time and choose the max to be the clock time if the stages are dependent on previous stages? Again, the values are dependent, but the way that we're designing this is whenever you register something, then you don't care about the previous stage, okay? So all you care about is that between 2 stages, this combinational logic T has to be enough such that it settled down between the clock cycle goes to the next one, okay? I'll explain that next time as well, so hopefully that will answer some of your questions. Someone says that we are adding more register. Is it fair to assume we are making a power usage trade-off? Yes. So we are actually adding a lot of more power to our system, but we get lots of benefits for that. Could you explain? Yeah, so somebody says this approach lets us pipeline, but the CPU time remains about the same. Why do you care about the CPU time if it's not that good of an indicator of CPU performance? No, actually, it's a good indicator of CPU performance. That's what we care. As I said, CPU time is the number that we care, and we want to reduce CPU time, okay? But what is happening is that with the current format of pipelining, unfortunately, CPU time will not decrease. It actually stays the same. Next time I'm going to show you how to do that, how to fix that problem. Okay. All right. I think that's it. Let me stop the recording.